So controlling traveling wave phonons at room temperature, essentially what this translates to is controlling sound with light. And I'm excited to tell you about the ways in which we've done this and show you the results from experiments I've performed. But first, I want to explain what this means and the underlying principle of how this can occur. So the underlying phenomenon is called Brillouin scattering. Brillouin scattering is a nonlinear optical phenomenon that involves coupling between light and sound, or optomechanical coupling. And essentially, I'm going to unpack this, but essentially, we inject laser light of a given frequency, which we call the pump, into a material where it has the opportunity to inelastically scatter with the mechanical oscillations in the material, or the sound. This is essentially a collision, an inelastic collision between two bodies. A photon, one quantum of light, is called a photon, and a phonon, one quantum of mechanical oscillation, or sound, is called a phonon. And in this collision, energy and momentum are exchanged. Now, some of you know that I'm a big fan of physical demonstrations and analogies, and so I'm going to try to quickly offer an analogy that you can carry with you through the talk to try to understand this otherwise kind of complex coupling process. I promise this will be worth the time. Here I have a weight with side weights that are specially tuned, and it is allowed to move up on the spring up and down. So if I inject this system with a little bit of rotational energy and let it unwind, we see that the weight with rotational energy begins to spin, and because of the tuning between the two coupled oscillations, energy begins to transfer to longitudinal motion of the spring. And eventually, if I've done my tuning correctly, the weight nearly completely stops spinning, and then the energy then is transferred back from longitudinal motion to purely rotational motion of the weight, which is nearly what I've accomplished here. This is an energy momentum exchange process similar to what occurs in Brillouin scattering. The light in Brillouin scattering can be thought of as the rotational energy, angular frequency of the light. It's kind of a good analogy. And the traveling wave phonons, longitudinally traveling wave phonons, are analogous to the up and down longitudinal motion of the spring. Now, in order for this coupling to occur between the rotation and the longitudinal, or the light and the sound, there needs to be a careful rate matching. So the rate of oscillations need to match. So the rate that the weight spins, the rate that the weight spins at needs to match the rate, the natural rate of the up and down motion of the spring. In Brillouin scattering, this is also the exact same phenomenon. The phase velocity of sound needs to match the phase velocity of light. Now, of course, we know even in a material, the speed of light is much faster than that of sound. And so in order to get the speed of light to match that of sound, what we do is we let a second optical field called the Stokes optically interfere with the pump. And the resulting optical beat note is the difference frequency of the pump and the Stokes. So if you select the pump and the Stokes frequencies somewhat close to each other, the difference frequency is actually not that fast, and it can match that of the sound. So you have that rate matching, phase velocity matching, phase matching. If I mess up the tuning of this system here, and I perform the exact same, inject some rotational energy here, and I let it go, let me see if I can get it exactly where it needs to be. Then we would see that the weight spins, but almost no energy is transferred vertically, although I didn't really let it go where it is, but maybe you're convinced that it will just simply spin in place, and the only up and down motion is what I just didn't set the weight to, and it doesn't efficiently transfer all of its energy to the up and down motion. So it is an inefficient energy momentum exchange. A similar thing occurs in Brillouin scattering, whereby we have to meet the phase matching requirements. And if you were to scan across a selection of pump Stokes frequencies, or the tuning of the side weights here, through the perfect resonance phase matching condition, what you would get is a plot of energy momentum exchange that maps out a Lorentzian function, whereby the y-axis here can very loosely be said to be the efficiency of energy momentum exchange in the coupled modes of oscillation. So that hopefully gives you an idea of what the underlying process is that underpins all of the experiments and results that I'll be showing. Now I'm going to take a couple moments to get this out of our visual space. All right. So I'm going to be talking to you about three main projects and experiments that we worked on. The first is laser cooling of traveling wave phonons in an optical fiber. This is a first demonstration of laser cooling in optical fiber. This is essentially quieting sound with light. Second, I'm going to tell you about a new process that we developed called coherently stimulated Brillouin scattering, or COBS. This is essentially amplifying sound to measure subtle signals that were previously unmeasurable. And finally, I'm going to tell you about the direction that we pointed this instrument to explore a space between a Brillouin regime and a Raman regime, a continuous and discrete regime, which is essentially harnessing sound for engineered behavior. So first up, laser cooling. Why do we care about laser cooling? A lot of photonic devices that are used in data centers and for information and signal processing are performance limited by thermal noise that are present in the photonic circuits in which they are employed. And so if we can reduce the thermal noise of photonic circuits and quiet the systems, their performance is enhanced. Also, a new emerging kind of frontier of application of laser cooling is to be able to access quantum regimes. If we can start a material already pre-cooled to a certain amount, laser cooling may be able to push it the rest of the way down to the ground state of the material, near 0 Kelvin, to be able to perform quantum experiments in the acoustic domain. This is applied this has previously been demonstrated in cavity resonance systems. So if you can carefully engineer a resonant cavity or cavity to support n integer multiples of the wavelengths, then you can tune a laser just read of the cavity's resonance, and the cavity then facilitates an efficient coupling process at the cooling sideband of the laser frequency. So this was well understood for decades in discrete systems where, again, n integer multiples of frequencies are allowed through these carefully designed resonator systems. But about 15 years ago, researchers began to wonder if this same cooling phenomenon could be applied to continuous media, like bulk materials and extended waveguides, such as optical fiber. And this is inherently rather challenging, because ultimately any optical refrigeration technique, laser cooling technique, needs to be able to satisfy this fast escape condition, whereby very simply we have to have the light that has stolen the mechanical energy from the system leave the system before the material replenishes that stolen mechanical energy. So its natural dissipation rate, given by gamma naught here on the right side of the expression, needs to be slower than the average time of the light to leave the system. And this is especially challenging in continuous media because the scattered power, what describes the strength of the cooling interaction, contains length So the longer the interaction length, the more, the stronger the laser cooling process. Some of these terms are relevant here and will show up as characters later in our story. So especially pertinent is gain, GB. This is the Brillouin gain. This is the material property that describes how responsive a material is to optical stimulation. P sub P is the pump power, the injected pump power, and L is the length. This is a spontaneous scattering process. So the last term there indicates the thermal phonon occupation. A landmark study came in the form of a paper by Otterstrom et al. In 2018. They demonstrated for the first time laser cooling in a continuous media in a very carefully engineered chip waveguide with cross-sectional geometry to achieve extremely high effective Brillouin gain, so 270 per watt per meter. So this number is basically per some amount of watts of injected pump power, and per some interaction length, here is the scaling coefficient for how strong the process is. This is particularly challenging if we try to move into the fiber regime, because typical single mode fibers offer extremely low material gain. So on the order of 10 to the negative 3 for typical single mode fibers. And what we really need is a high enough gain such that we can reduce the interaction length short enough so that we meet the fast escape condition, so that we can have the light come in, steal the energy, leave the system before the system replenishes that thermal energy from its surrounding mechanical energy, from the surrounding thermal bath. The solution to this problem comes in the form of carbon disulfide. Now, of course, this is not an optical fiber. However, carbon disulfide offers very high gain, and we can very cleverly inject carbon disulfide into the hollow core of an optical fiber, thereby facilitating a very high bulk gain from the carbon disulfide and tight constriction of light and sound in the core of the fiber, and have a very high effective gain of this fiber. So about 6 per watt per meter, much less than the 270 from the Otterstrom paper, but sufficient to meet our fast escape condition. So here we see a schematic where you have single mode fiber with a larger core being tapered down by UHNA7. This is a smaller core fiber to closely mode match the mode field diameter of our apparatus to the smaller field of the, mode field diameter of the hollow core. So I want to show real quick pictures of what this looks like in real life. We can see the optical fiber going really thinly across on the left picture here. And we have a reservoir centered over the splice between solid core and hollow core fibers. And there is an almost unnoticeable gap here where carbon disulfide can enter. This was like the wedge open part in the diagram from the previous picture. And through capillary action, carbon disulfide is allowed to enter into the hollow core and fill the length of the hollow core fiber. So here it is on the right in the picture. We see it taped down on the optical table and integrated into the system. So now that the stage is set, let's talk about cooling figure of merit. So if we can perform this experiment, what would we be looking for? How much cooling can we accomplish, and how would we measure this? Well, all materials, as I've stated, have a natural rate of mechanical dissipation. This is gamma naught, right? And to cool is to increase that dissipation rate. So if you're dissipating energy faster, you're at a cooler state. And it turns out that spectral line width gives a measure, a window into the dissipation rate of materials. This essentially is a consequence of the time, energy, uncertainty principle. The more localized an event is in time, the necessarily more widened or broadened the energy distribution. And energy is contained in the frequency of a wave, right? And so what we're looking for is a broadened line width as a measure of cooling. If we see with increasing application of laser cooling, a broadening of line widths, then we have achieved cooling. So I want to dive into this just a little bit into the physics here. On the left expression, we have a quantized phonon dissipation rate, where n is essentially the number of phonons, given by the Bose-Einstein distribution, or equivalently the Planck distribution for phonons. And we have the dissipation rate again. So it's the rate of phonons leaving the system. And this is on the left side here. This is after laser cooling has been applied. So this is a broadened line width. And here is the equilibrium case. And what's neat is for our frequencies and around room temperature, KBT is much larger than h bar omega, allowing us to apply a first order approximation, which reduces this n term quite considerably. Plugging it back in, we get a ratio of the broadened to natural line width of the spectra being approximately equal to the equilibrium temperature and the effective cooled temperature. Rejiggering this to get it in terms of the temperature difference from equilibrium to cooled temperature, we arrive at our figure of merit for evaluating how much cooling it has occurred. This is what I've termed in my dissertation the C value, or percent cooled. This fractional amount cooled per starting temperature is a better figure of merit than what has traditionally been reported in papers, because the degree of cooling that can be achieved with the same process and the same parameters gets harder and harder the cooler your material starts at. And so while your absolute or raw temperature change will appear to give diminishing returns, the percent cooled will remain an important figure of merit. So this is important for quantum experiments as you start cooler. All right, so real quickly, I'd like to go over the experimental setup here. We have a laser, which emits light at frequency omega. And we have a split by power. Following the top line, we have this light from the laser amplified by the upside down triangle there, and power controlled by a variable optical attenuator. It's essentially an optical valve. It then routes through the circulator, which is like a roundabout where you have to take the first turn. So we're coming down here, take the first exit. It injects into the liquid core optical fiber, whereby the backscattering process occurs. The light goes in, energy momentum transfer occurs, steals the energy, and exits faster than it's replenished. And we are taking that energy in the form of light back through, retraverses through this circulator. It's filtered so that we can cut out any unwanted noise, and it recombines here in a process called heterodyne spectroscopy with a fresh instance of the pump frequency. And the reason for this is twofold. So one, there's a gain process that occurs because it's a multiplication of the amplitudes, but more importantly, the optical frequency of the laser, even shifted by the sound frequency, is way too fast for electronics to be able to read. It's in terahertz. And so in order for this to be able to be read in by our photodiode, we need to step that frequency down. So we again employ the exact same concept of taking an optical beat note, letting these two frequencies interfere, and you get the difference frequency. Difference frequency being exactly that frequency of sound here. That is incident on the detector, amplified in the radio, and observed by the spectrum analyzer, where we look for width changes to indicate cooling. Here are, as glimpsed earlier, a collection of spectra taken for this experiment. So what we see here is as the blue color fades, we are increasing and ramping up our optical refrigeration strength. So with increasing pump power or applied optical refrigeration, we are looking for the widths to increase. Here I've plotted the extracted line widths from those spectra we were just witnessing. And we see that with increasing pump power, indeed, there is a broadening of line width, and it follows a linear trend as would be expected before reaching any pump depletion effects. So reintroducing our cooling figure of merit here, we find that we have cooled a band of traveling wave phonons in fiber by about 27 Kelvin, or about 9.3%. That would be the C value. All right, so I've just told you about laser cooling of traveling wave phonons in optical fiber. This is essentially quieting sound with light. Now I'm going to move into talking about the coherently stimulated Brillouin scattering process that serves to amplify sound to measure subtle signals. Brillouin spectroscopy is a measurement process whereby you can obtain mechanical properties of materials. So if you're interacting with sound with light, sound is indicative of mechanical properties of properties of material. And we can obtain the mechanical resonances, sound speed, elastic moduli of materials by employing different scattering techniques. And this is employed in, out in the field in the spaces of biomechanics, drug discovery, medical diagnostics, also on a larger scale, distributed fiber optic strain and temperature sensing. So we have a process that is sensitive to stresses and resulting strains on physical structures. Bridges and fences and things can be monitored over large scales with Brillouin, distributed fiber optic Brillouin spectroscopy. Now, in traditional Brillouin scattering, it comes in a couple different flavors. Spontaneous Brillouin scattering, interacting with the natural thermal fluctuations of a material. This is the process that we were employing for the laser cooling. We came upon a material at its natural temperature, and we were not amplifying anything. Instead, we were using spontaneous Brillouin scattering, the cooling sideband of a process, to cool. And this is based off of the thermal phonons within a material. But if we employ this pump and Stokes process and turn pump powers up high enough, or inject a small Stokes seed into the material, optical field, we can induce the self-reinforcing amplification process, whereby the pump scatters with the acoustic field in the material, causing a self-selected phase-matched Stokes term to appear. And that Stokes term, that Stokes light, then beats with, creating an optical beat note, beats with the pump that then serves to reinforce the acoustic field, which then causes more Stokes and then causes more reinforcement of the acoustic field. And there's a exponential increase in this process up to a point of pump depletion effects. But and that's pretty good, but wouldn't it be nice if we could just skip to the chase, cut to the chase, and inject a very high power Stokes field of our own, right? Just inject a high power laser right at the Stokes frequency and just pummel the acoustic field, beating it up very high immediately, right? Instead of letting the gradual kind of process of pump Stokes and stimulated in traditional stimulated Brillouin processes. However, the problem is easy to witness here. The exact same signal that you would be measuring is at the same frequency as that Stokes field that you're injecting. So if you're blasting the material with something that has, contains no information about the mechanical information of the material, and then you try to collect a, much smaller than 1% of the exact same frequency, which does contain, the Stokes field just drowns it out. You cannot separate out the Stokes frequency. Okay, so maybe we can get a little bit clever and introduce a new laser, a new optical field. So maybe we can have the pump and the Stokes pummeling this acoustic field, driving up the phonons, right? And then we'll just introduce a probe which is shifted in frequency a little bit to go in and interact with the driven phonon. And then we will collect this shifted backscattered probe light, shifted a little bit from the Stokes, so we can distinguish. Well, the problem is that in general, it would not be coherent. The process would not be phase matched, and the two would not talk to each other. So the pump and the Stokes would be driving one phonon mode, and the probe would be just completely missing it, not be interacting with it, not phase matched. However, given that that we have an uncertainty principle which speaks to the more localized in space, the more necessarily broadened in momentum, we can actually enter this regime for very small interaction lengths, which translates to short length samples, whereby we get a little bit of wiggle room. So a certainty in position, right, of our acoustic field translates to an uncertainty in momentum. And the momentum of a wave is given by its wave vector, which can be related to its wavelength all the way off to the right, this delta lambda term. This provides our wiggle room. This speaks to how much we can separate the probe from the pump, employing our sneaky technique of introducing another laser frequency to be able to pummel that acoustic field and still, with our separate laser, retrieve mechanical information from the material. So this is essentially cheating phase matching because of the uncertainty principle that is at play. So if we get lengths short enough, so if we're a 1 meter sample, which isn't that short, we get a pump probe detuning of 0.6 picometers, not very much, but this still preserves 50% of the signal. This is meaningful, right? And if we go shorter for a 1 centimeter sample, pump probe detuning of 36 picometers, that's separation of pump and probe, right? That's our wiggle room. It preserves 83% of the signal. That's very significant because 36 picometers, that separation, is about 4.5 gigahertz at our wavelengths. And so that is enough for a spectral filter to be able to pick off our scattered light, to be able to retrieve the mechanical information and distinguish it from the driven Stokes field that we're pummeling the system with. This is coherently stimulated Brevon spectroscopy. This is the art underlying the instrument. It allows a Stokes driving field to really strongly drive up the acoustic phonon mode while preserving coherence with a shifted probe, be able to pick off that information. And it turns out that for typical parameters, it is about 1 million times more powerful than traditional SBS. Here is the respective scattered powers for the 3 flavors of Brevon scattering. We have our spontaneous, stimulated, and now our Cobb's scattered power process. And because this doesn't really do much for our brains to stare at, I've plotted and modeled each for identical parameters, whereby you can see that scattered power for a range of smaller lengths, especially around 1 centimeter. The pink line representing the Brevon spectrometer that we've developed, this Cobb's process, dominates and wins majorly by orders of magnitude over the next best method across a range of different lengths here. I'm not going to go through the schematic, but I'm very proud of this diagram, and I just wanted to bring it up here to illustrate the complexity underlying the principle, but I'd like to keep the talk on the salient physics that underpins it. But I thought this was kind of neat to show this is the actual instrument schematically, and this is the actual instrument on the optical table at one point or another. And I'm going to withhold some of the eye candy of results and measurements from this instrument because I'm going to show them in the form of telling the next story of where I decided to take this Brevon spectrometer that is especially good at measuring things at small lengths and where I decided to point it. So I've told you about laser cooling. I've now told you about the Cobb's process. Finally, we're going to talk about Brevon-induced Raman modes. So this is harnessing sound for engineered behaviors. So we pretty well understand the Brevon regime now. It's scattering with traveling wave phonons, historically in bulk material, but any extended material, a waveguide or fiber. This is excitement of a continuum of modes, a band of phonons in extended media. There's another regime called Raman scattering, which is more closely related to what I started off talking about with the resonant cavity, where laser cooling had been employed. And this is not traveling wave phonons, but standing wave phonons. And originally, and historically, this was the oscillations between atoms in molecules. So you can employ analogous Raman spectroscopy techniques to obtain chemical information about material, because each chemical bond has a specific frequency that it vibrates at. So we have this kind of continuous domain in Brillouin scattering, and we have this discrete n integer multiples or very specific one frequency allowed, not a continuum or band of frequencies regime with Raman scattering. But we know from wave physics that a traveling wave phonon can overlap with its same frequency in the other direction and cause a standing wave, right? So traveling waves can become standing waves by auto-interfering. And so I became fascinated with the transition, the middle space between Brillouin and Raman domains. If we have something that can measure at very small lengths, perhaps we have the ability to measure small enough lengths that the traveling wave phonons, which don't last very long, do not travel very far, micrometers in most materials, perhaps might be able to reach the end of a sample and reflect at the interface and interfere with the other traveling wave phonons, causing a standing wave to be formed, or a standing wave pattern to be formed in the material reminiscent of Raman modes. So these would be like a continuous type regime collapsing down into a discrete regime. We know each of the poles very well, those are understood, but what is the transition and where does it fold over? I became really fascinated with that. So we are starting in the Brillouin regime and slowly approaching the Raman regime by shrinking the lengths. So this is an illustration of what I was just talking about, with a traveling wave phonon reflecting at an interface within a small length sample that we have integrated into our Cobb's system to auto-interfere with itself and create a standing wave pattern inside the material at n integer multiples of its wavelength. So a Raman-like frequency would be the speed of sound divided by the traversal of the length of the media at n integer multiples. These would be your discrete modes, but formed by our traveling waves, right? So Brillouin-induced Raman-like modes. So in order to pull this off, I want to bring your attention to the bottom here, the bottom expression again. In order to pull this off, this is the scattered power that we get from our Cobb's spectrometer. And we have a Brillouin gain that scales with the square, but we have a length, interaction length that scales with the square. Or we have a scattered power that scales with the square of length, sorry. Which means that if we're turning the length parameter down, this becomes quadratically more difficult to measure. So a 10 times smaller interaction length, 10 times shorter sample for given parameters and gain translates to a 100 times harder measurement. So a 10 times shorter sample, 100 times harder to measure. So what we need in order to pull this off is as high of everything else as we can get, right? We're ramping everything up, turning every knob to 11 because we need that length as short as possible. So the Brillouin gain factor, we want to choose materials that offer the absolute highest Brillouin gain possible. And we're going to, obtain as much lab equipment as possible to crank the optical powers up as high as possible. And the sync squared term is just that detuning, that wiggle room. So we're going to set that appropriately for the length. So in this spectrum of materials here, we have UHNA3. This is germanium doped optical fibers. So it's a little bit better than typical standard fibers. The effective Brillouin gain given in the middle here is 0.6 per watt per meter. Next we have tellurium dioxide, which is 1.1 per watt per meter. That is the effective Brillouin gain. So this is the material that comes in kind of a powdered form that can be physically evaporated to be deposited onto substrate to form a chalcogenide glass, tellurium glass. And then we have our good old carbon disulfide, the effective Brillouin gain being a little bit better, 1.65 per watt per meter. And finally, we have this exotic material off to the right, which is the unoxidized tellurium, offering this comparatively grand term, 14.4 per watt per meter. This ended up being elusive and not working out. There's a story behind that you can ask me. All right, so now begins the fireworks show of the end of the fireworks show, whereby I send off all the results at once. So we're tuned to pay attention to the lengths, understanding that a 10 times shorter length translates to a 100 times shorter measurement. So here we have our germanium doped optical fiber, 0.6 per watt per meter Brillouin gain. And you can see it measured out here in the top left corner. And here is its resulting spectra at the resonant frequency, 9.18. Most beautiful Brillouin spectra you're going to see. Step down, 10 times shorter, 100 times harder. We get 1 millimeter of UHNA3. This picture may not be able to capture quite as well, but this marked with a pen, small black dot, is measured to be 1 millimeter of this special fiber sandwiched between normal fiber. And here is a measurement. We see a tiny bit of asymmetry starting to come into play. This is a result of Phonon interference, which is just indicative of the fact that the signal is so small that it is on the order of the background continuum that exists underlying in the photonic circuit. And they interfere, and their relative phases cause this asymmetry. So none of the details of that matter as much as the fact that if you see some asymmetry, it is certainly indicative of the fact that the signal was about at the edge of the instrument's ability to measure things at the time. And in between each of these measurements, I am making improvements and finding insights about how to improve the signal to noise ratio of the instrument to push it to further and further limits. All right, so now we move from the fiber integrated regime of optical fiber and into a free space regime, which offers a little bit less tight confinement of light and sound. So the effective gain is a little bit harder. And we're limited by the lenses and the optical geometry going on. And here we see a cuvette filled with carbon disulfide, offering a 1 centimeter path length in the beam path of the instrument. And we see significant asymmetry here due to that Phonon resonance. This, by the way, I want to emphasize, maybe a little bit dramatically, but previous measurements that I had showed here, world record, not achieved at room temperature before this occurred. 10 times smaller, 100 times harder, another world record, right? It could be phrased in this way. Moving over to carbon disulfide, world record at room temperature, because this instrument offers things that were not available before, right? Going down to 4 millimeters of carbon disulfide in free space, you rotate the cuvette by 90 degrees, and it offers a 4 millimeter path length. Here's a very clear spectra, another world record. Now we jump to a very thin film of tellurium dioxide, 1 micron thickness, evaporated onto a glass slide via physical vapor deposition in a laboratory upstairs. And you can see that while the spectra is not as clean as the 1 centimeter of UHNA3, there is still very clear evidence of a measurement here exactly at the frequency that we expect. Interestingly, when I took this measurement, I discounted it for a couple reasons, one of which being it showed a little bit more line width than I was expecting. So for a TeO2, tellurium dioxide crystal, we would expect a line width of about 10 megahertz. This shows a line width of about 40, maybe 50 megahertz. And so I discounted it as maybe some sort of noise or artifact in the spectra. However, through writing my dissertation and re-evaluating data deeply, I looked deeper into the process of physical vapor deposition and deposited films, and the amorphous nature of deposited films, the grain sizes of tellurium dioxide that would certainly result in a larger dissipation rate of deposited tellurium dioxide as compared to its crystalline counterpart. With perfect crystal structure, the phonons can last much longer, whereas they dissipate faster if the material is amorphous and deposited onto a film. And it is absolutely plausible that we would see a line width around 40 to 50 megahertz, thus bringing this measurement back into attention. Also, the resonance matches exactly what we would expect the resonance to match to be for tellurium dioxide. I had performed a follow-up experiment on this independent measurement on tellurium dioxide, 1 micron again, whereby I removed the sample and took a measurement of the underlying background. And you can see that there is a small bump around that region. And that was one of the reasons why I tossed the measurement aside originally. But you can see in the raw data, as well as binned to 5 megahertz and 10 megahertz, the light blue, representing when the sample was in the instrument, stands above to a significant level, the background, the underlying background, and clearly indicates a measurement. As mentioned, at the time, I did not understand that, I did not recognize this as a measurement, and so I had backed up to a more familiar carbon disulfide and obtained shorter path length cells. Here is a measurement of 1 millimeter carbon disulfide. And here's a measurement of 100 microns carbon disulfide. You can see this thin glass cell standing up in the beam path of the instrument, offering 100 microns of path length of carbon disulfide, indicating a clear measurement. This is beyond any doubt, a measurement of 100 microns carbon disulfide, indisputable. And this represents a world record of Brillouin scattering of longitudinally traveling phonons at room temperature because of this enhanced process. And then in the past many months, I've spent a great deal of time learning how to employ our chip scale waveguides, or chip waveguides, into our system and measure them. It requires very careful tuning and alignment of the optical fields to the chip. So on the left, we see an SEM image of a face of a early waveguide that I connected with a group at BYU, Dr. Aaron Hawkins, and they were interested in trying to connect our science to their waveguides that they are able to produce of many different materials and shapes and geometries. And there was a collaboration that formed and a deep learning process that started because of the great opportunity that was offered there. And the light here is guided on this wide rib that is suspended above an air channel here. And this is on the order of microns. And so preliminary measurement of this chip waveguide shows the light blue is with the chip and the dark blue is without the chip. You might be interested in why the background in this one without the chip shows such a sharp, background peak here. That's because the rib that the light is guided in is silica. This is a silica rib waveguide. And silica is glass, and that's what our apparatus is made out of. So all the single mode fiber that exists in our apparatus also offers its own resonance, and the instrument can measure itself. It's kind of a cool thing to say in the first place, but it becomes annoying when you're trying to measure something that sits right on top of that resonance. But here we see very clearly the waveguide offering a spectral peak that stands above the underlying resonance from the instrument itself. All right, So I told you about how we achieved laser cooling of traveling wave phonons in optical fiber, quieting sound with light, and how that metric is extracted from the line widths of the spectra. I told you about the coherently stimulated Brillouin scattering process and the instrument that employs it. And finally, I showed you the process or the domain that I was trying to explore with this instrument of this crossover point between Brillouin traveling waves to Raman to get down to short enough lengths. And progress, preliminary progress was certainly made in that direction. I'd like to thank everybody here at NAU, especially everybody in the physics department that helped all of this become a reality. I'd like to thank the Center for Integrated Nanotechnologies at Los Alamos and Sandia National Labs, who participated deeply in the process of the tellurium portion of this research, providing a way for that to actually happen. And I'd like to thank Dr. Aaron Hawkins and everyone at BYU for their help in helping me learn how to integrate the chip waveguides, which would be an ideal next direction to take this research. I believe that provides the paradigm to be able to achieve what I was setting out to achieve, short path length going from Brillouin to Raman with our instrument. And I'd like to thank you all for coming. And I'll take any questions that anybody has. I'll put it back to the slide that jogs memory of the salient research results and experiments that I covered. Yes, Bob.
Yeah, what are the noise ratios you're getting?
Yeah, so the sensitivity is best characterized by the minimum amount of scattered power that we can detect and show a signal. So if you turn the power down for a given material as low as possible, how much scattered power can we detect for an acceptable SNR, right? So we can control the signal to noise if we turn the powers up drastically, like for some of the spectra I showed earlier. Exceptional SNR, but really we want to see the sensitivity of the instrument. So if you turn those powers down, you can turn it down so that there's no spectra and you're just seeing noise, of course, right? So for an SNR of about 5, I show that the instrument has a sensitivity of sub 10 femtowatts. So the scattered power that we are able to recognize with this instrument as a measurement at 5 SNR is sub 10 femtowatts, really closer to 5. 10 is conservative.
Joel, could you repeat the question?
Oh, yes. The question was, what SNR are we achieving with this instrument? Ultimately, what sensitivity, what performance metric from this instrument are we able to achieve? Excellent question. Yeah.
Were you ever able to conclude that you were seeing Raman light interference?
Yeah, no. Yeah, so we got close on many different materials, but the lengths that are required are related to the mean phonon travel distance in a given material. So it's different for different materials. For carbon disulfide, the phonons travel an average amount of length of about 5 microns. So we got to 100 microns in carbon disulfide. Far gap to get down to 5. I had a 10 micron cell that I exhaustively tried to measure in, but even we would have to go half of that more. In tellurium dioxide, it's something around 250 microns, but seeing as I had not recognized this measurement as being a thing at the time, I didn't take that 1 micron measurement and run with it to try to explore to see if I saw those modes. So maybe with a tellurium dioxide film, certainly with a tellurium dioxide crystal, which offers a cleaner environment to host this, which is perceivable, we probably would be able to see these Raman modes, which occur at discrete resonant frequencies, like a frequency cone. Yeah, good question. Yeah, Jaime.
So when you're talking about the tellurium dioxide having a larger line width,
Yes.
you mentioned that it has to do with precipitation.
Yes.
I was wondering, how why it was.
Okay, yeah, it's the same concept. Okay, so the question is, sorry, I forgot to repeat the first question, but maybe you could gather from context what they are asking of why I didn't achieve Brilon to Raman transition, these Raman modes. This next question is, what is the connection between that dissipation rate and specifically the tellurium dioxide film to the line width, and why can we conclude this, this analysis of an amorphous deposited film translating to a wider line width? It's the exact same concept as with the laser cooling. So line width provides a direct window into dissipation rate because the more localized in time the phonon exists for, the shorter it exists for, that means that it has been dissipated faster, right? And a more localized in time phonon offers a wider spread in energy, time energy uncertainty principle, which is a kind of a mathematical uncertainty principle relating a consequence of Fourier analysis, ultimately.
Am I correct in assuming that the state of matter would affect it?
The state of matter affects the line width. Yes. So yeah. So temperature can affect line width. Certainly, depending on what states you're talking about, certainly the structure of the matter can affect the line width. Certain things wouldn't probably affect too much, but yeah, certainly temperature. Yeah. Question?
What temperature would you kind of like consider room temperature, and when would it start like swaying where you're starting to skew?
Yeah, well, so that's an excellent question. That's an excellent question. And one of the reasons why I tried to nail down that C value that I've kind of termed for the cooling is, what is room temperature? If you're in a lab in the Arctic versus your lab here, there might be a nice 10 or 15 degree swing. I've taken room temperature for the cooling experiment to be 293 degrees Kelvin for that day. In terms of how temperature might swing something, I can offer maybe the most dramatic temperature change that occurred in my research. I'm not sure if I will be able to easily share this in short order, but I want to bring this other slide up whereby, oh, actually, no. Whereby, I don't think I included it. The story about the tellurium is relevant here. So that extra exotic material that offered 14.4 per watt per meter, I chased that because I wanted that gain, right? And it took a large effort to be able to deposit that and have it stick onto the glass. The story was we were able to deposit it, but then it would immediately just kind of flake off. So then I reached out to CINT, the Center for Integrated Nanotechnologies, assisted by Dr. Jen Martinez, one of my committee members, and got connected with an expert there, Alessandro, who helped me understand that there needs to be an adhesion layer between the tellurium and the glass in order for it to stick properly. And a proper adhesion layer is usually offered by selenium. It's just another element that can be deposited, but it's highly toxic, and so it requires this whole environment. So we couldn't do it here. They sent us primed samples with 10 nanometers of selenium for an adhesion layer, providing glue between the glass slide and the tellurium to be able to stick. I was thrilled. I would be now able to deposit my tellurium, have it stick to the slide, and put it into the beam path of the instrument, and get that 14.4 estimated gain factor. However, in doing that, the optical fields absorbed into the material enough to then oxidize the tellurium, turning it back into tellurium dioxide. And you can see, I should have included a picture, but there's a little chip with a little spot, dark material tellurium around, and light tellurium dioxide right in a circle of the beam path. So all the effort, months, and multiple PhDs involved in preparing this tellurium deposited film to then measure, ultimately it just reoxidized and got me right back to tellurium dioxide. But yeah, so that's a dramatic temperature effect because it was absorption of the optical fields that caused that change in the material. So we have to be kind of wary about all these different matter states and effects. Yeah. Yeah, thanks for letting me tell that story. Any other questions? Honey, yeah.
How did the optical
Yeah, that process of that sample fabrication dominated my life for a number of months. The challenging part was getting the splice such that it didn't fully seal, but also wasn't so separated that as soon as you breathed on it, it would break, which is pretty close to how they ended up. And a number of different, iterative experiments of finding the ideal splicing parameters for this were arrived at. And so the way that we would fill it is once the sample was constructed, you have a reservoir that sits directly over the splice, and you simply just put carefully, because even just a heavy drop of carbon disulfide right on the splice a number of times broke the slice. So I would drip carbon disulfide down the side of the vial, of the inside of the vial. Here we see. And I would fill that vial with carbon disulfide, and it fills naturally via capillary action through the small core of the carbon disulfide. And this process, when I arrived in the lab, was demonstrated, but ripe for optimization. And I went through a number of, as I mentioned, iterative experiments to try to improve the performance and the reliability of these samples, reduce time and material costs in the process of fabrication. And so one of the things that I learned from this is, this process of filling takes hours, and it is it drops off, non-linearly. The time takes longer and longer, exponentially longer and longer to reach the end. First few centimeters fill in seconds. You can watch it. It's actually kind of cool. But then it takes hours and hours to fill the rest of the way, and we would do a meter sample. And so when I came into the lab, standard procedure typically would accidentally deem a sample dead when it was maybe 10 or 15 centimeters yet to reach the end. It was thought that perhaps it reached the end and then experienced some sort of phenomenon that had it back off, and that you had to catch it at the right moment. Instead, I basically sat in a dark room under the fume hood for more than 24 hours, sleeping on occasion and checking it off a timer on my phone. Lived in that room for about 30 hours, just watching it. And I verified, no, it never reached the end and then backed off. It just needed about 6 more hours and it would reach the end in these kinds of cases. Different fill rates, filled according to the splice gap and such. And so, every sample that starts filling ends filling. You just have to wait. And so that was one of the insights among many others. Yeah. Good question. Thanks for letting me tell that story. I forgot to repeat the question, but it was asking about the fabrication process of the liquid core optical fiber sample, of course. Any other questions? Yeah.
I just have a question on that tellurium oxide slide where you're showing how show the graph with the tellurium in the system, and then how it looks kind of similar when you remove the tellurium samples from the system, how it had the same sort of general shape. So
this one here,
was like one of the motivations or was one of the findings from it just like that tellurium oxide that like enhanced like the overall like signal that you're getting from the noise?
Well,
or, like,
the
shape does very clearly look like the shape stays the same, or just like the titanium or tellurium oxide, like just enhance the amplitude for all those different points.
Yeah, so let me clarify that. Thanks for the question, John. So he's asking about this measurement here and how the background does show a feature. And the 1 micron tellurium dioxide measurement also shows a feature, and they kind of have this similar formation. That's just an unfortunate coincidence. There happens to be some noise there. It's actually incredible how often that happened, where exactly where I'm looking for something, there happens to be just some background blip. Gabe, one of our research collaborators, can attest to more than a couple handfuls of times that has occurred. And so, to clarify what's going on here, then without sample is just a measurement of the background, just the underlying spectra caused by the noise that exists in the photonic circuit as it is. The light blue here is a measurement of with the tellurium dioxide present. So anything that rises above the background will be would be significant. So here we see that blip a little bit, but we also see that the measurement of the tellurium dioxide rises considerably above, indicating a strongly plausible measurement. That's how to interpret this data. Yeah. John, by the way, helped in a lot of the process of deposition. He's an expert in the physical vapor deposition system, works in the lab where where a lot of these samples were made. And so thanks for your help on this. Any other questions? Excellent questions from everybody. I really appreciate that.
Okay, so now we'll move on to the closed part of this, so we can see the audience.